Across the world for the past 15 years, a growing body of leading simulation experts in both the CAD and CAE industries have been on a quest to develop superior simulation technology based on splines, which is the same fundamental building block used in CAD. When you go to these conferences, they've now published thousands of papers, and you'll come across the venerable fathers of B-splines and T-splines and various finite element methods. This is now the hot area for development for simulation techniques. They're joined by a young army of mathematicians and geometers and analysts who are all on this quest to develop what they call isogeometric analysis, or coming up with a geometry definition that's suitable for both simulation and CAD. So just as a frame of reference before you continue on, CAD, the fundamental building block, is a smooth spline, whereas simulation, it's more of a faceted element. And this vision of isogeometric analysis is a single source of truth for both design and analysis. And it's an amazingly compelling vision, motivated by the rough interplay today between CAD and simulation techniques and the fact that as simulations get more complex, these standard FEA elements get painfully brittle. That's illustrated by the automotive industry, where there's a fairly linear process from evolving a concept through design to manufacturing. It's all spline-based. But to run a simulation, it's time intensive. It takes several weeks and budgets of millions of dollars to make an approximation of the CAD model. And then it doesn't make much sense to run these algorithms such as contact and crash that are highly sensitive to the geometric accuracy on a less accurate mesh model. So the only recourse that these companies have is to make very detailed mesh models, which increases computation time and makes these simulations the most expensive jobs run on the HPC units in these companies. So maybe you're an analyst who's lucky enough to work on simple problems that can be generated by automated meshing, but for hard problems, these issues persist across industries. So just imagine how powerful it would be if there was this single source of truth that was valuable for both CAD and simulation. There'd be a really high business value with more accurate simulations, time-saved modeling. And what my partners and I have realized when we started Coreform several years ago to kind of pursue this path is that as a starting point, merely bringing the accuracy of splines to simulation brings significant value. So today we have some prototype software that allows for the integration with both legacy mesh data from sources such as LS-DYNA and Nastran, as well as integrations with next generation CAD data from programs like Autodesk Fusion 360. We can pull that into our new preprocessor called Coreform Process, where we convert this to analysis-suitable spline data that can be used either in Coreform Analyze, which is the industry's first native spline-based simulation technology, or we can also send this to legacy software, which is starting to be retrofit to support splines. So LS-DYNA is one instance of a legacy solver. They're one of the leading crash solvers used that has also seen the value of high accuracy splines in simulation. So today I'd like to talk about some of the business value that you can see from running spline-based simulation, because better simulation comes through better geometry. So you get better accuracy in less time, increased robustness, lower simulation costs, and this can happen with minimal change to your workflow. So a lot of the examples that you'll see today, our software is currently in closed beta. We work with customers who see what we're doing, recognize that they have limitations they're bumping into with the brittleness of FEA elements in their industries. They feed us problems, we implement that in our software, give them access to it, and that's how we're kind of developing. So if any of these seem familiar to you, I'd love to talk with you, and we'd love to work with you as well to solve your problems using the software. And I think by the end of this presentation, you might be able to understand why some of the early reaction to this has been quotes like this from an FEA expert user. Spline-based simulation is clearly the future. Everything is better than FEA. You see this and you just go, wow. And the head of an automotive crash department said that this has the potential to solve difficult, previously unsolved problems for us because of its superior properties to FEA. So one other thing I'll just kind of talk about is our positioning before I continue. When you compare traditional FEA tools to new tools being developed, you've seen a lot, even today, of tools that are targeted more at designers that try to make simulation more accessible, which is often at the cost of accuracy. We're doing completely the opposite. We're focusing on the hardest problems. This is specifically ones that analysts are most interested in. But as you'll also see that as fundamental as this technology is, as this continues to mature, we see the breadth of application going across the entire domain of finite element analysis today. So let's start talking about some of the business value with a number of simple benchmarks. So this is one that was provided to us by Honeywell, and this is just a very simple spring compression simulation, and some of the requirements that they had was that there'd be a very small number of springs, only 5 of them would ever be manufactured, but they'd have to work for 100 years. So they need to be very confident in these simulation results. So our partner started out by just using a standard automatic TET meshing algorithm, and that produced an unusable mesh. It needs to be a higher quality to actually capture the helical shape. So then they went and more methodically created, using partitioning, a hex mesh, and this hit their level of accuracy, but it required nearly 250,000 elements to capture this detailed curvature of the helical shape. And there's some of the elements at the end have a high aspect ratio, which is not ideal for simulation. So this ended up taking them 24 hours to run on 16 cores. Now you see the power of smooth splines really shines in an example like this. So this is a view into our beta Coreform process preprocessor. What we're able to do here is define parametrically exactly the spline shape of this spring. So we're able to, this is in a web browser, it can run in the cloud or behind your firewall, and we're able to define within the acceptable level of tolerance this exact spring with only 500 elements. Again, that's compared to nearly 250,000 with linear FEA because splines are smooth. You can capture smooth data. So once we've captured this, we can go ahead and run the simulation. And the simulation only took us 8 hours on a single core. And this was an implicit dynamic contact algorithm. Again, that's compared to their commercial solution, which they had to run explicitly and took far longer. So with this result, we got done 50 times faster with 500 times fewer elements than linear FEA, again, just because of the power and robustness of smooth splines. But the benefits go even farther and can be, again, illustrated with a very simple example. So in the aerospace industry, then stress is a very important quantity to measure. If the stress if the stress computed is off by just 10%, that can lead to like a 50% miscalculations of fatigue, which can be a fatal error. So I'm going to take a look at this simple benchmark that I think Richard from ANSYS mentioned earlier this morning, the infinite plane with a hole cut out. And what we're able to show with splines is that we can accurately solve this benchmark within an acceptable error with only 16 elements. This is with quadratic splines, so we can accurately represent that circle. In comparison, FEA took 16 times that many elements to achieve that same level of accuracy. Splines are also more robust for large deformations. So when you look at a structure such as even this very simple column, you think, okay, well, I can accurately represent that with FEA because it's just a rectangular right now. But once you apply a deformation, then splines, the robustness of splines really shines. You can see as we just do a torture test twist of this, we fix the bottom, we just twist the top until it fails. The FEA solution dies sooner, and then the spline definition was able to complete many more time steps, 44% longer. So this robustness of splines, it still means that to solve hard problems, you'll still need good analyst expertise, but that expertise will be able to be employed actually solving the hard problems of dealing with the frailness and brittleness of FEA elements. Another example of splines used in large deformations, this is just a flex cable being bent. This is, if you can imagine, a customer that has hundreds of flex cables and they need to bend them all to determine if there's going to be too much fatigue over the life of the flex cable as it's assembled. The other tricky part of this is after it's bent, then there's temperature applied, and at some point this might wrinkle. And depending, again, on how much fatigue is applied and the temperature, that can lead to failure. With splines, we're able to converge at a far smaller number of nodes with only 5,000 nodes to converge on the accurate temperature. Whereas with FEA, with this full model, these customers were spending millions of nodes, and that was making the problem almost intractable to be able to run simulations on all of the different flux cable lines, even though it's a very expensive issue for them if it gets wrong. So by using splines, it just makes these simulations less expensive to compute, and you get higher accuracy. So I'm going to pause just for a second to talk about, there's all these powerful benefits of splines, And I've already told you there's been thousands of research papers written about this over the last 15 years. So you may ask yourself, well, why is this not in every single commercial software yet? And the issue has been the lack of having a spline definition that's suitable for complicated unstructured meshes. And so at Coreform, we invented U-splines to fit this need. So U-splines satisfies both the smooth requirements of CAD, where B-RIPs are traditionally used, and the watertight requirements of analysis, where they traditionally use meshes. So another benefit of T-splines is it's also compatible with other spline types like B-splines and NURBS, and also T-splines. This was my former company. I sold to Autodesk, and here's an example of a complex T-spline part modeled in Autodesk Fusion 360. Some of the benefits of T-splines are the ability to have T-junctions or hanging nodes, extraordinary points, creases and sharpness in the same model. U-splines takes us to the next level, whereas this is one single degree 3 T-spline. With U-splines in the single model, we can have degree 1, degree 2 to have exact fillets, degree 3, arbitrary degrees, which is intriguing from a design standpoint, but from a simulation standpoint, one of the surprising benefits is that this decreases simulation cost for complex simulation problems like explicit dynamics. In explicit dynamics, the whole cost of the simulation is determined by the time steps. How many time steps does it take? Like how large are your time steps and how expensive is each time step to compute? Interesting with U-splines, we can exploit the ability to have multiple degrees in the same surface to tune this to have ideal time steps. I'll just show this again on a simple fracture benchmark, which again is an area where simulation on smooth splines really shines. We're just going to clamp one end, apply velocity to the other end, use a phase field method to determine the crack formation, and then you can see the crack after that. But the interesting thing is examining the splines versus the FEA. With the same number of elements, and again, this is oversampling for splines because we only require a fewer number of elements than FEA because we can capture curvature better, we can have a higher, significantly larger time step, in fact, 40% larger time step with U-splines than with linear FEA. That's kind of counterintuitive that you'll be able to perform the simulation faster with splines. And we can also smoothly capture the fillet, which again is crucial for stress and fracture simulation. So how can you actually bring this into your workflow? Well, you can get maximum benefit with very minimal change. We're able to insert this both into current FEA workflows by leveraging the meshes that you already have, and then also build this with next generation workflows. So let's take a look at Nastran, one of the most venerable formats for FEA. Traditionally, if you just make a Nastran assembly, you run a simulation on that mesh. We can take that same Nastran assembly and with the unstructured U-splines, convert each of those parts to a smooth U-spline model. We can convert the connectors as well, the loads and boundary conditions, and run a spline-based simulation right on that same mesh model. So you can use your existing data. We do the same thing with other mesh formats such as LS-DYNA. You can read in a car hood in this instance, convert that to a smooth U-spline, and again, run a simulation either in our solver, or we can actually export back to LS-DYNA, who's also adding spline-based capability that benefits greatly from U-splines for unstructured meshes. I really like this example. This is a gear defined exactly in Fusion 360. This one happens to be defined with T-splines, but you could use NURBS as well. Export this just using a standard IGES or STEP file format, and then you can read this directly into Coreform process where you're defining the boundary conditions and loads directly on the exact spline geometry that you define. This is not an approximation. This is not a mesh. And then you run the simulation directly on this CAD model. And that's really powerful for contact because this is more robust. The simulation doesn't die as quickly as it would with finite element linear meshes. It's more accurate per degree of freedom, and this is a contact algorithm that we run on an extremely coarse mesh that we define in CAD ourselves. So again, in conclusion, splines provide better simulation through giving better geometry. This gives better accuracy in less time, increased robustness, lower simulation cost, and this can happen with minimal change to your workflow. So I end with a limerick. Old school simulation, goodbye. There is a new method to try. It's accurate, robust, its results you can trust. Spline-based simulation is nigh. Thank you.